40 million times every second, inside a ring buried 100 meters beneath a field in Switzerland, two clouds of protons pass through one another. Almost everything that comes out of those collisions gets caught. 7,000 tons of steel and silicon sit wrapped around that point for exactly that purpose. But not everything gets caught. Some of what comes out goes straight through all of it, and out the far side without touching a single atom, and the only evidence it was ever there is a hole in the arithmetic, a wedge of the machine where every instrument reported that nothing arrived. So something is escaping down there, constantly, and always has been. The question tonight is what? And underneath it sits a stranger question. Is there a kind of escape that the most sensitive instrument ever built could never, by its own design, notice at all? By the end of tonight, you will know exactly what the answer to that is. Settle in, subscribe if you have not yet, and stay with us, because the road to that answer runs through a letter a man was embarrassed to have written, a Nobel Prize awarded for measuring nothing, and one direction no upgrade can ever fix. Let's begin. Part 1. The Night. The machine stopped. On a Saturday in June of 2026, the most powerful machine our species has ever built was switched off, and the last thing it did before the lights went down was fail to see something. That sentence is going to sound like a criticism. It is not. Failing to see something is, as it turns out, the single most valuable thing that machine does, and understanding why is going to take us the next 2 hours. Let me set the scene properly because the scene matters. Underneath the border between France and Switzerland, about 100 meters down, there is a tunnel shaped like a ring. It is 27 kilometers around. If you could walk it at a comfortable pace without stopping, it would take you the better part of 5 hours to get back to where you started. Inside that tunnel there is a pipe, and inside the pipe there are two beams of protons travelling in opposite directions at a speed so close to the speed of light that the difference is measured in meters per second rather than percentages. Those beams are steered by superconducting magnets cooled to a temperature colder than the space between stars, and they are focused down to a width narrower than a human hair, and 4 times around that ring they are made to cross. On the 27th of June, 2026, the last of those protons went around for the final time, and then the beams were steered out of the ring and into a block of graphite and steel designed to absorb them. That was the end of what physicists call Run 3, the third long data-taking period in the machine's working life. The tunnel is not being abandoned, it is being rebuilt. The accelerator has entered a multi-year program of upgrades that will eventually turn it into something more capable still, and beams are expected to return around 2030. But for now, the ring is quiet, and it will stay quiet for years. Here is what that machine produced across its lifetime, and I want to be careful with the number, because it is easy to say and hard to feel. It delivered close to 550 inverse femtobarns of what is called integrated luminosity. That unit does not measure energy. It measures opportunity. It measures the accumulated number of chances for something rare to happen. One inverse femtobarn corresponds very roughly to 100 trillion proton-proton collisions. So 550 of them is a number of collisions with no useful comparison in ordinary life, and the machine was originally designed to deliver only 300. It nearly doubled its own design specification. The two general-purpose experiments sitting on that ring, the ones called Atlas and CMS, each recorded something like 540 inverse femtobarns of that total. What I want you to hold on to is not the number. It is what the number now means. The archive is closed. Every collision that machine will ever produce in its current configuration has already been produced. Whatever came out of those collisions has already come out. Whatever left the building has already left. The question of what escaped is no longer a question you can answer by running the machine harder or longer or hotter, because the machine is off. It is now a question you answer by looking, very carefully, and for a very long time, at a finished record of things that are no longer happening. Imagine standing in the control center on that Saturday. There are people at consoles, and there is a countdown, which sounds dramatic but in practice is quite procedural, the way a pilot's landing checklist is procedural. Someone confirms the dump kickers are armed. The beams are steered out of the ring in a fraction of a millisecond, spread deliberately across the face of the absorber so they do not drill a hole through it, and dumped. On the monitors, the beam intensity plot goes to 0 and stays there, And then something quieter happens, something you would only notice if you were watching the detector rather than the accelerator. Down in the cavern, inside a 7,000-ton instrument the size of a small cathedral, the event rate collapses. A moment ago there were tens of millions of proton crossings every second. Now there is nothing but the slow background patter of cosmic ray muons drifting down through 100 meters of rock, a few per second, and the faint electrical hum of 100 million readout channels listening to a room where nothing is happening anymore. That is what the end of an era actually sounds like. It sounds like a machine that has stopped being interrupted. Now here is the strange part, and this is where the video really begins. In all of that data, across all of those collisions, across 4 years of running, and more than a decade of operation before it, one of the most sought-after things physicists are looking for is nothing. Not a small signal, not a faint signal, nothing. A place in the detector where every single instrument reported that absolutely no energy arrived, and where that absence is the entire result. Back in November of 2016, the Atlas collaboration published a short public explainer on its own website with a title so plain it is almost unsettling. The title was, "What Happens When Energy Goes Missing?" It was written by a physicist named Julia Gonski, who at the time was a researcher working inside Atlas's combined performance effort, in the group responsible for jets, and for exactly this problem. She is now a Panofsky Fellow and Associate Staff Scientist at the SLAC National Accelerator Laboratory in California, where her work focuses on new approaches to hunting for physics beyond the standard model, in particular using machine learning and anomaly detection, along with fast machine learning for the electronics that decide what a detector even bothers to record. Keep that last detail in your back pocket. We are going to come back to it in a way you will not expect. Her explainer opens with a boast that turns out to be a confession. Physicists at Atlas, she writes, like to consider themselves pretty decent at tracking down particles. In fact, they do it every day. Just because a proton-proton collision does not produce the next Nobel Prize winning particle does not mean it can be ignored. Teams of people are still combing through every single event, rebuilding known particles out of the signals they leave behind. And then comes the turn. Unfortunately, she writes, some particles are tricky. They do not leave any signal in the detector at all. Sit with that for a second, because it is a genuinely odd thing for an experimentalist to admit in public. There is a category of thing that this machine is built to find which is, by its nature, invisible to the machine. It goes in one side and out the other, and touches nothing on the way through. It does not deposit energy. It does not bend in the magnetic field because it carries no charge. It does not shower in the calorimeter. It leaves the 7,000 tons of steel and silicon and liquid argon exactly as undisturbed as it found them. Those invisible things could be something perfectly ordinary that we already understand. But, as she puts it, they could also be dark matter, one of the biggest mysteries in physics today. And so physicists really want a way to reconstruct these particles, which means, in her words, that they have to be even trickier. That is the whole of this video, compressed into a sentence. The instrument does not detect the particle. The instrument detects the shape of the particle's absence, and then it rebuilds the particle out of the shape. I find that idea genuinely beautiful, and I also find it, the more I sit with it, quietly alarming, because a method built entirely on measuring nothing has a very specific kind of failure mode. It can only ever notice the kinds of nothing it is capable of noticing. Everything else looks like a perfectly balanced, perfectly ordinary, perfectly boring collision. Which brings us to the question we're going to spend the rest of tonight answering, and I am going to pose it now and then deliberately refuse to answer it until the very end. Is something escaping that machine? And if something is, could there be a kind of escape that our best instrument, by its own design, is physically incapable of ever noticing? Before we can go anywhere near that, we have to back up. Because to understand how anybody could possibly measure a hole, you first have to understand why a collision is supposed to balance at all. And the picture that almost everyone carries in their head of what happens when two protons hit each other turns out to be wrong in a way that changes everything. Part 2. Not billiard balls. The picture almost everybody has of a particle collider is two things hitting each other head-on. Two little spheres, flying toward one another down a tube, meeting in the middle and shattering. It is a clean image. It is the image every animation uses, and it is wrong in a way that turns out to matter enormously for everything that follows. A proton is not a sphere. A proton is not really an object at all, in the sense that a marble is an object. A proton is a bound state, which is a physicist's way of saying it is a relationship rather than a thing. Inside it there are quarks, the fundamental particles that give the proton its identity, and there are gluons, which carry the strong nuclear force that holds the quarks together. And the gluons are not passive. They are constantly being emitted and absorbed and splitting into pairs of quarks that annihilate again, so that at any given instant the interior of a proton contains a shifting population of constituents that is genuinely difficult to pin down. All of those constituents together carry the momentum of the proton as it hurtles down the beam pipe. And physicists have one word for anything inside a proton that carries momentum. They call it a parton. Richard Feynman coined the term in the late 1960s, and he coined it deliberately vaguely, because at the time nobody was certain what was actually in there. Parton just means the thing that carries a part. It was a name chosen to avoid committing to a picture, and it stuck. So the collision is not two billiard balls meeting on a table. It is a handful of billiard balls colliding with another handful of billiard balls. Things get, to put it mildly, hectic. And here is the detail I need you to file away, because it is going to come back at the very end of tonight and rearrange everything you think you have understood. Nobody knows how the proton's momentum was divided among its partons at the instant of impact. Not approximately, not roughly, not in any given collision. The division is described only by probability distributions called parton distribution functions, and those functions are measured rather than derived. They come out of decades of scattering experiments in which people fired electrons at protons and studied how they bounced. They are among the largest single sources of theoretical uncertainty in everything a Hadron Collider does. When two protons meet, you know exactly how much momentum each proton carried in total, because you built the accelerator that gave it to them. You do not know how much of that momentum was in the specific quark that actually did the colliding. It is worth pausing on where those probability distributions actually come from, because the story is a good one. In the late 1960s, at the Stanford Linear Accelerator Center, experimenters fired very high-energy electrons at protons and looked at how they scattered. If a proton had been a soft uniform blob of charge, the electrons would have been gently deflected. Instead, a small but significant fraction of them came bouncing back at wide angles, as though they had struck something small and hard buried inside. It was the same result, and very nearly the same shock, as Rutherford's gold foil experiment half a century earlier, which had revealed that atoms contain a tiny dense nucleus. The proton had an inside. Decades of increasingly precise versions of that experiment, at ever higher energies, are what produce the functions we use today. Nobody derived them from first principles. People measured them, one careful scattering experiment at a time, and we are still measuring them. Hold that. Just set it down somewhere you can find it again. Let me try to give you a sense of the energies involved, because the numbers are misleading in both directions. During run 3, the beams collided at a combined energy of 13.6 trillion electron volts, which is the highest collision energy ever achieved in a laboratory anywhere on Earth. That sounds enormous, and in the world of particle physics it is. But an individual proton at that energy carries roughly the kinetic energy of a flying mosquito. That is not a joke, and it is not a trick. A mosquito in flight and a proton at the highest energy humans can produce carry comparable amounts of energy. The difference, and it is the entire difference, is concentration. The mosquito spreads that energy across something like 100 quintillion atoms. The proton concentrates it into a region less than a quadrillionth of a meter across. That is what makes the collision extraordinary. It is not the amount of energy. It is the energy density, and the density is high enough that for a fleeting instant, in a volume smaller than an atomic nucleus, conditions resemble those of the very early universe, and particles that have not existed naturally anywhere in the cosmos for 13.8 billion years can briefly wink into being before decaying away again. Now, the machine that watches this happen. Atlas is about 46 meters long and 25 meters across and weighs roughly 7,000 tons, which is comparable to the Eiffel Tower. It is built in layers, like an onion, wrapped around a point in space where two hair-thin beams cross. And its entire design philosophy can be summed up in one sentence. It is trying to be a sphere that nothing can get out of. Working outward from the collision point, there is first a tracking detector made of silicon, sitting inside a powerful magnetic field, which records the curving paths of charged particles without absorbing them. From how sharply a track curves, you get the particle's momentum. Then come the calorimeters, and this is where the philosophy gets brutal. A calorimeter measures energy by stopping the particle. Dense absorber material makes an incoming particle shower into a spray of secondary particles. That spray is sampled by active layers, and the total signal tells you how much energy went in, which means the calorimeter works by destroying what it measures. It is the only way. You cannot weigh a bullet in flight, you have to catch it. There is one particle that refuses to cooperate with this arrangement, and that is the muon. Muons are heavy relatives of the electron, and they punch straight through the calorimeters almost untouched, carrying most of their energy out the far side. That is why the outermost layer of Atlas, the layer that gives the detector its size, is an entire second detector devoted to nothing but muons, a spectrometer the size of a cathedral wrapped around everything else. A very large fraction of the 7,000 tons exists because of one stubborn particle. There is one more object I need to introduce here, because it is going to do a great deal of work later on, and that object is the jet. When a quark or a gluon is knocked out of a proton, it cannot travel on its own. The strong force does not weaken with distance the way gravity and electromagnetism do. It gets stronger, so that pulling a quark away from its neighbours costs more and more energy until, at some point, it becomes energetically cheaper for the universe to simply create a new quark and antiquark pair out of the vacuum than to keep stretching the connection. That happens over and over, cascading, until what began as a single quark has become a tightly collimated spray of dozens or hundreds of ordinary particles all flying in roughly the same direction. That spray is a jet. In the detector it shows up as a cone-shaped shower of energy, and reconstructing it means gathering up all those separate deposits and deciding, by algorithm, that they belong to one original thing. Jets are the most common interesting object at a Hadron Collider, and they are also the least precisely measured, and both of those facts are going to matter. The word physicists use for how completely a detector wraps around the collision point is hermeticity. A perfectly hermetic detector would cover every possible direction, the full sphere, with no gaps at all, so that anything leaving the collision would have to pass through something instrumented. Hermeticity is the entire foundation of the technique this video is about, because if you want to notice that something left without being seen, you first have to be certain you saw everything else. And here I have to be honest with you in a way that will matter enormously later. No real detector is fully hermetic. Not one. Not Atlas, not CMS, not any collider detector ever built or ever proposed. Every one of them has gaps, and the gaps are not distributed randomly. I am going to leave that there for now, because we have not yet earned the reason why. But I want you to notice that I said it. So this is our situation. We have a collision between two objects that are not really objects, made of constituents whose momenta we know only statistically, producing a spray of particles into a detector that is trying and slightly failing to be a closed sphere. It sounds like a mess. In one direction, along the beam, it genuinely is a mess. But there is one plane in which the arithmetic is not a mess. There is one plane in which the arithmetic is exact and clean and admits of no argument whatsoever. In that plane, the books must balance to zero every single time, without exception, and they must do so for reasons that have nothing to do with our models or our simulations or our assumptions, and everything to do with a law that has survived every test physics has ever thrown at it. That plane is where this entire method lives, and once you understand why the books must balance there, you will understand how it is possible to draw a picture of something that was never there. Part 3. The plane. Where the books must balance. Everything about the method we are building toward rests on a single geometric fact, so let me lay it out slowly. The two partons that actually collide are travelling along the beamline. That is where their momentum is. They are moving forward or backward along the axis of the tunnel, and they have essentially no momentum at all in any sideways direction. Whatever tiny transverse motion they carry from bouncing around inside their parent protons is negligible compared to the enormous forward momentum the accelerator gave them. So before the collision, if you look at the plane perpendicular to the beam, the plane that slices the detector like a coin, there is nothing moving in it. The sideways ledger reads 0, now they hit. In a genuinely head-on collision between 2 point-like objects, the products do not tend to continue along the original direction. That is what you would expect from a glancing blow, a graze, where things carry on more or less the way they were already going. A truly central collision throws material outward, perpendicular to the line of approach. Physicists call that perpendicular plane the transverse plane, and it is where the interesting products of a hard collision end up. So look at what we have. Before the collision, essentially zero momentum in the transverse plane. After the collision, a great deal of material moving around in that plane, jets flying outward, electrons, muons, photons, sprays of hadrons, sometimes dozens of reconstructed objects, and conservation of momentum says that all of it, every last vector, must add back up to zero. I want to be precise about the status of that statement, because it is not the same kind of statement as most of what gets said in a physics documentary. This is not a model. It is not a fit to data. It is not a simulation that has been tuned until it agrees with observation. Conservation of momentum is one of the most rigorously tested propositions in the whole of science, tested continuously, at every scale from planetary orbits to particle decays, for 300 years, and it has never once been observed to fail. In modern physics, it is not even really an assumption. It is a consequence of the fact that the laws of physics are the same here as they are 1 meter to the left, which is about as basic as a statement about the universe can get. So what the transverse plane gives an experimenter is something almost nobody in any other field of science ever gets. It gives them a closed accounting identity. The books must balance. Not usually, not on average, exactly, in every single event. And that means something remarkable. If the books do not balance, that is not noise. That is not an error bar. That is information. Here is the way the Atlas explainer puts it, and I have not seen it put better anywhere. Go back to the pool table. 2 clusters of billiard balls come together and scatter across the felt, and you watch this happen a few times, and it all looks perfectly ordinary. Balls go this way and that way, and if you added up all their motions, you would find they cancelled out, because that is what balls do. Then you see one collision after which every single ball you can see flies off in the same direction. All of them. Together. To the left. That would look profoundly unnatural to you, and you would be right to feel that way. You might genuinely believe that you saw every ball that emerged from that collision. But their behaviour is impossible on its own terms, and so their behaviour forces you to a conclusion. Something else must have crossed that table going right. Something you did not see. In a billiards hall, depending on the sort of establishment you frequent, there are generally no ghost balls. In particle physics, there very much are, and the ghosts most of the time are neutrinos. We are going to spend a whole section on where neutrinos came from and how much trouble they caused, but for now all you need is this. A neutrino is a fundamental particle that interacts with matter so rarely that it treats 7,000 tons of steel and silicon and liquid argon as though it were not there. It goes in, it goes out. Nothing in between registers a thing. But it is not nothing. It carries momentum, and it took that momentum from the collision, and the collision noticed even though the detector did not. So here is the procedure, and it is almost insultingly simple to state. You add up all the particle vectors you can actually see. Every jet, every lepton, every photon, every scrap of leftover energy. You add them up in the transverse plane, and whatever the total comes to, you assign the thing you could not see exactly enough momentum pointing in exactly the opposite direction to bring the sum back to zero. Then you draw that vector. You draw an arrow representing a thing you never observed, whose magnitude you calculated from things you did observe, pointing into a part of your detector where absolutely nothing happened. Let me put you inside one for a moment. You're looking at an event display from Atlas. It is a cross-section, a circular slice through the detector taken looking down the beam pipe, so you're seeing the transverse plane head-on. The concentric rings of the tracker and the calorimeters are drawn as coloured bands. Scattered around the circle are the deposits from this particular collision, and 2 of them are large. 2 jets splayed apart, each drawn as a thick blue arrow pointing outward from the centre, each one representing a shower of energy caught in the calorimeter and reconstructed by software into a single object. And then there is a third arrow. It is red, and it does not correspond to anything in the detector at all. No cluster of energy sits at its tip. No track leads into it. If you traced it outward from the centre and looked at the readout channels it passes through, every single one of them would tell you the same thing, which is that nothing arrived here. Zero. Silence. The red line was not measured, it was calculated. Its length and its direction are precisely whatever they need to be, so that when you add it to the 2 blue arrows, the 3 of them cancel exactly. It is the shape of the hole in the sum, That is what I mean when I say the red line points at nothing. It is the only arrow in physics that is drawn by measuring everywhere else. The name for that vector is missing transverse energy, which is the older phrasing you will still hear people use, or missing transverse momentum, which is the more careful modern term, written in papers as PT miss and pronounced in corridors, universally as simply met. And I want to flag something about it that gets lost in the popular telling. It is not a number, it is a vector. It has a magnitude, which tells you how much momentum the invisible thing carried, and it has a direction, which tells you which way it went. Very often the direction is the more diagnostic half. Where the red line points, relative to the visible objects, is what distinguishes a genuine invisible particle from a jet that was simply measured badly, and that distinction is going to become the hinge on which the second half of tonight turns. Building that red line in practice means assembling a very particular inventory, and it is worth walking through it, because the inventory is where the difficulty hides. To calculate the missing transverse momentum for a single collision, Atlas combines every fully calibrated object the detector managed to reconstruct. Electrons, muons, photons, tau leptons that decayed into hadrons, hadronic jets, and then, crucially, one more category that has no glamour attached to it whatsoever, which is the soft activity from all the remaining tracks that never got assembled into any named object at all. The crumbs, the particles too low in energy, or too scattered, to belong to anything the reconstruction software was willing to give a name to. That last term is called the soft term, and it is the hardest part of the entire measurement. It is a large number of small contributions, each one individually negligible and collectively decisive, and it is exquisitely sensitive to conditions in the detector that have nothing to do with the collision you actually care about. There is also a bookkeeping problem that sounds trivial and is not. The same deposit of energy in the calorimeter can plausibly belong to more than one reconstructed object. An electron leaves a shower. That shower might also get swept up by the algorithm that builds jets. If you then add both the electron and the jet into your sum, you have counted the same energy twice, and your red line is now pointing at a hole that does not exist. So Atlas runs what is called a signal ambiguity resolution procedure, which is a formal set of rules deciding, deposit by deposit, which object gets to claim each piece of energy, and rejecting any input that has already been used elsewhere in the sum. Every fragment of energy is counted exactly once, or the whole thing is worthless. And then there is a choice to make, which physicists resolve by refusing to make it. Rather than settle on one definition, Atlas defines several different missing momentum working points, with selections of varying strictness about which objects and which soft tracks are allowed into the sum. The tightest of them improves the resolution of the measurement, under the most crowded running conditions by up to 39% compared with the loosest. But strictness is not free. Every tightening that makes the measurement cleaner also throws away real events that would have passed a looser cut. There is no setting that is simply correct. There is only a trade you have to choose consciously and then live with. So that is the technique. That is the whole conceptual core of how the most sensitive instrument ever built goes looking for things that leave no trace. It does not look for them. It looks at everything else with obsessive completeness, and then it works out what shape of hole is left over. It is elegant. It is genuinely one of the more beautiful ideas in experimental science. It is also, the moment you try to do it in a real machine made of real materials with real gaps in it, an absolute nightmare. And before we get anywhere near what has been found, we need to talk about how anyone can possibly trust a measurement of nothing at all. Except that first, I want to take you back 96 years to a man who did exactly this with a pencil and a piece of paper, and who was so embarrassed by what he had done that he refused to publish it. Part 4. A Desperate Remedy. I called this technique modern, and it is not. Inferring an invisible particle from a hole in the accounting is the oldest successful gamble in particle physics, and it began, as most good ideas in this field do, with a crisis that nobody could solve. The crisis was beta decay. In beta decay, an atomic nucleus spontaneously emits an electron and turns into a different element. It was one of the first radioactive processes ever identified, and by the 1920s it was being studied with real precision, which is when the trouble started. Here is what should happen if the world is sensible. You start with a nucleus in a particular state, with a particular energy. You end with a different nucleus in a particular state, with a different particular energy, plus one electron. The energy released is the difference between the two nuclear states, and that difference is a fixed number, set by the physics of the nucleus. The electron has to carry it, so every electron emitted in that particular decay should come out with the same energy. Not roughly the same, exactly the same. It is arithmetic, not opinion. What the experimenters actually found was that the electrons came out with a continuous spread of energies. Some emerged with almost nothing, some emerged with the full expected amount. Most came out somewhere in between, distributed across a smooth curve. There was a maximum, and the maximum matched the prediction exactly, which made the whole thing worse rather than better, because it meant the calculation was right and the electrons were still coming out wrong. The obvious escape route was that the energy was going somewhere unobserved. Perhaps the nucleus was also emitting gamma rays that nobody was catching, and each decay divided the energy between the electron and some radiation that was slipping past the instruments. That was a reasonable guess, and it was tested. James Chadwick had done crucial early work establishing the continuous spectrum. Later, Charles Drummond Ellis and William Worcester performed what is essentially the definitive experiment, using a calorimetric method. They wrapped the radioactive source in a thick absorber and simply measured the total heat produced. If unseen gamma rays were carrying the missing energy, the absorber would catch them and the heat would come out right. The heat did not come out right. The heat matched the average energy of the electrons, not the maximum. Whatever was carrying the missing energy was not being stopped by lead. So this was the situation at the end of the 1920s. Energy was disappearing. Not once, not sporadically, but every time, in measurable and reproducible amounts, in one of the most common processes in nature, and nobody could say where it went. Niels Bohr proposed a solution, and I want you to understand who was making this proposal before you judge it. Bohr was not a fringe figure. He was arguably the most influential physicist alive, the man whose model of the atom had opened the quantum era, whose institute in Copenhagen was the intellectual centre of the entire field, and whose opinion on any question of quantum theory carried more weight than anyone's. His proposal was that energy conservation is not exactly true. Specifically, that in the subatomic world, energy might be conserved only statistically, holding on average across many decays but capable of being violated in any individual one. It sounds outrageous now. It did not sound outrageous then, because quantum mechanics had already dismantled so many other things that everyone had assumed were absolute, and there was no particular reason to be confident that conservation laws would survive the demolition. Wolfgang Pauli could not accept it. Pauli was a formidable figure in his own right, famous within the field for a critical faculty so merciless that colleagues joked about the Pauli effect, the tendency of experimental equipment to break when he walked into a room. And his objection here was not sentimental. It was that the principle of the conservation of energy had stood the test in every field of physics anyone had ever looked at, over centuries, without a single confirmed exception, and that throwing it away to fix one anomaly in one process was a worse cure than the disease. So he proposed an alternative, and on the 4th of December 1930, he sent it in a letter to a conference of nuclear physicists gathered at Tübingen. The letter is addressed, with the kind of arch humour Pauli was known for, to the dear radioactive ladies and gentlemen. His idea was this. During beta decay, in addition to the electron, the nucleus emits a second particle. This particle is electrically neutral, which is why nobody had detected it, and it carries away whatever energy the electron did not take, so that the sum of the two energies is always the same fixed number the calculation predicts. The spread in electron energies is not a violation of anything. It is just the two particles dividing a fixed total between them in different proportions each time. The missing energy was not missing, it was leaving in something's pocket. That is, in every essential respect, the same move that Atlas makes today when it draws a red line into an empty wedge of a detector. Add up what you can see. Assign the remainder to something you cannot. Insist that the books balance because the books must balance. But here is the part of this story that I keep coming back to, and it is not the physics. Pauli was appalled at himself. In the letter he describes what he has done in his own words. He says that he had recourse to a desperate remedy in order to save the exchange theorem of statistics and the law of conservation of energy. A desperate remedy. That is his phrase for his own idea, in writing, in the document proposing it. And he did not publish it. This is the detail that gets me. One of the most consequential proposals in the history of physics, And Pauli did not write it up as a paper and submit it to a journal. He put it in a letter. Because as far as he could tell, he had done something close to an intellectual crime. He had invented a particle that could not be detected purely in order to protect a law he refused to abandon, and he had no way to test it, and by his own reckoning that made it something less than proper physics. He's reported to have said to a colleague, in something like despair, that he had done a terrible thing, that he had postulated a particle that cannot be detected. And then there is the last detail, which is so human that it almost undoes the whole solemn weight of the thing. Pauli did not deliver this proposal in person. He did not go to Tübingen at all. He explains in the letter that he could not attend because he was indispensable in Zurich, on account of a ball on the night of the 6th and 7th of December. He proposed an undetectable particle, apologized for it in writing, called his own idea a desperate remedy, declined to publish it, sent it to a room he was not in, and then went dancing. I want to slow down here, because this is the emotional centre of the first half of tonight, and it deserves more than a fact. Think about what it takes to write that letter. You are one of the sharpest critics in your field, a man whose professional reputation rests on demolishing sloppy reasoning in other people, and you have just talked yourself into proposing an entity that by construction nobody can see. You cannot photograph it, you cannot deflect it, you cannot count it. Your entire evidence for its existence is that the alternative, which is that a 300-year-old law occasionally fails, feels worse to you. There is no experiment on Earth that can tell you whether you are right. You may have just invented a ghost to protect your own aesthetic preferences, and you know it, and you say so, in the document, in the phrase, desperate remedy, and you send it anyway. That is what intellectual courage actually looks like from the inside. It does not feel like courage. It feels like embarrassment that you decided to go through with. And Pauli was right. All of it. The particle is real. It is the most abundant particle with mass in the universe, and about 100 trillion of them are passing through your body as you listen to this, arriving from the core of the sun, having left it 8 minutes ago and crossed 150 million kilometers of space, and then the entire thickness of the Earth if it happens to be night where you are, and not one of them will touch a single atom of you. In an average human lifetime, perhaps one neutrino will interact with your body. One, out of a number with more than 20 digits in it. The particle needed a name. Pauli had originally called it the neutron, which was a perfectly good name until 1932, when James Chadwick discovered the actual neutron and took it. Enrico Fermi supplied the replacement in Italian with a diminutive, calling it the neutrino, the little neutral one. Fermi then did something more important. In 1934, he built a full quantitative theory of beta decay around Pauli's particle, one that made real numerical predictions about decay rates and energy spectra, turning a bookkeeping device into a testable piece of physics. He submitted it to the journal Nature, which rejected it, on the grounds that it contained speculations too remote from physical reality to be of interest to the reader. And then Hans Bethe and Rudolf Peierls did the calculation that everybody dreaded. They worked out how strongly this particle would have to interact with ordinary matter, given the observed rate of beta decay, and the answer was that a neutrino could pass through several light-years of solid lead with a good chance of not touching anything. Their conclusion, published, was that there is no practically possible way of observing the neutrino. So there it stood. A particle proposed by a man who was embarrassed to have proposed it, named by a colleague, made rigorous by a theory a major journal had refused to print, and declared undetectable in principle by two of the best calculators in the field. It stayed that way for 26 years, and then a telegram arrived in Zurich. Part 5. Everything comes to him who knows how to wait. For a quarter of a century, Pauli's particle was exactly the thing he had feared it would be. It was a number that made the ledger balance and nothing more. It appeared in equations. It made Fermi's theory work. It correctly predicted the shape of the beta spectrum, which is not a small thing. But it had no independent existence that anybody could demonstrate, and the best available calculation said it never would. There is a particular kind of scientific purgatory in that. You have an idea that explains everything it was invented to explain, that has never been contradicted, and that cannot be checked. It is not wrong. It is worse than wrong. It is unfalsifiable, and every year it survives on those terms is a year in which the field quietly wonders whether it has been fooling itself. Two people decided to try anyway. Their names were Clyde Cowan and Frederick Rains, and they were working at Los Alamos in the years after the war. Their reasoning was straightforward, in the way that impossible engineering problems often are. Beth and Piles had shown that any individual neutrino is almost certainly not going to interact. Fine. Then do not rely on any individual neutrino. Find a source that produces them in absolutely obscene quantities, put a large enough detector in front of it, and wait for the arithmetic to save you. If your odds are 1 in 100 billion trillion, you simply need more than 100 billion trillion attempts. Their first serious idea for such a source is worth stating out loud, because it tells you something about the era and about how badly they wanted this. They seriously proposed detonating a nuclear device and putting their detector nearby. The plan was worked out in some detail. A shaft would be dug, the detector would be dropped down it in free fall at the moment of detonation so that it experienced no shock, and it would land in a bed of feathers and foam rubber at the bottom, having recorded, they hoped, a handful of neutrino interactions during the microseconds when the flux was highest. They talked themselves out of it, not on grounds of taste but on grounds of physics, when they realized a nuclear reactor would give them a steadier, cleaner, and continuously available source of the same particles. It is a rare thing in science to abandon a plan involving a nuclear explosion because a simpler option turned out to be better. They built first at Hanford, in Washington state, and the results were suggestive but not convincing. The background was too high, so they built a bigger and better instrument and moved it to the brand new P-reactor at the Savannah River plant in South Carolina, and installed it in a basement room about 11 meters underground and only a short distance from the reactor core. The instrument itself deserves a description, because it is such a physical object in a story that has otherwise been about arithmetic. At its heart were tanks of water, into which cadmium chloride had been dissolved. The water supplied the protons in enormous numbers, simply by being water. Sandwiched around those tanks were larger tanks of liquid scintillator, a substance that gives off a flash of light when a charged particle passes through it, and staring into that liquid from all sides were racks of photomultiplier tubes, more than 100 of them, each one capable of registering the arrival of a handful of photons. The whole assembly was layered like a cake and weighed several tons. They gave the project a name that tells you exactly how they felt about their chances. They called it Project Poltergeist. The method they used is where the elegance lives. A neutrino cannot be caught directly, but it can be made to run the original reaction backwards. In beta decay, a neutron turns into a proton and emits an electron and an antineutrino. So an antineutrino that happens to hit a proton can, very rarely, turn it into a neutron and a positron. That process is called inverse beta decay, and the beauty of it is that it does not produce one signal, it produces two, separated by a specific and predictable interval. The positron annihilates almost immediately with an electron, producing a pair of gamma rays flying in opposite directions. The neutron wanders around for a few microseconds before being captured by a cadmium nucleus dissolved in the tank, which then emits its own distinctive burst of gamma rays. So what you look for is not a flash. You look for a flash, followed a few millionths of a second later by a very particular second flash. Nothing else in nature does that. Background radiation does not politely produce two correlated signals with the right delay. The reactor obliged with a flux that is hard to state casually. A large fission reactor pours out something on the order of 10 to the 20th antineutrinos every second, in every direction, unstoppably, as an unavoidable byproduct of the fission itself. There is no shielding for them, and there never will be. That torrent poured through the basement room and through the tanks and through Cowan and Rains themselves, hour after hour, and out of it, after months of running and painstaking work to beat down every source of accidental coincidence they could think of, they recorded a signal of roughly 3 events per hour. 3 per hour, out of 10 to the 20th per second. That is the ratio the whole enterprise turned on. On the 14th of June, 1956, they had it. Not a hint, not a suggestive excess. A clean, repeatable, unambiguous detection of a particle that 2 of the best theorists in the world had declared it was not practically possible to observe. There is a coda to the detection that most tellings leave out. Cowan and Rains were so aware of how easy it would be to fool themselves that they ran a control nobody had asked for. They took data with the reactor running, and then they took data with the reactor shut down, and they compared the two. The signal appeared when the reactor was on and vanished when it was off, exactly in proportion to the reactor's power. That comparison, more than any single event, is what made the result unarguable. Notice what the logic is. They did not prove the particle existed by seeing it. They proved it by turning off the source and watching an absence appear on cue, and the first thing they did was send a telegram to Zurich. The message told Pauli that they had definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. I like to imagine the moment on the other end of that wire. An elderly, famously acerbic theoretical physicist in Zurich is handed a telegram from two Americans he has probably never met, in a laboratory he has certainly never visited, informing him that the thing he apologized for inventing is real. He's reported to have interrupted the meeting he was in to read it aloud. Pauli's reply was 8 words long. Everything comes to him who knows how to wait. 26 years had passed since the letter to the radioactive, ladies and gentlemen. To give that a shape you can hold, a child born in the same week Pauli wrote that letter was 30 years old, with a career and probably children of their own, on the day the telegram was sent. Pauli himself would be dead 2 years later. He got his answer with almost nothing to spare. Frederick Reines received the Nobel Prize for it in 1995, 39 years after the detection and long after Cowan had died. And he gave his Nobel lecture a title that is, in 5 words, one of the best summaries of this entire idea anyone has written. He called it the neutrino, from poltergeist to particle. That is the arc. A hole in a ledger, taken seriously enough by enough stubborn people for long enough, turned out to be a real object with a real mass and real properties, one that we now use as a tool to look inside the sun and inside supernova and inside the Earth itself. And every single missing momentum vector drawn at the Large Hadron Collider today, every red line pointing into an empty wedge of a detector, is a direct descendant of that letter. The technique has not changed. Only the equipment has. But I have been telling you the reassuring version of this story, the one where patience is rewarded and the invisible thing turns out to be real. There is a stronger precedent than either of these, and it did not happen in a reactor basement in South Carolina. It happened at CERN 43 years ago, and it won a Nobel Prize with the words missing energy printed in the title of the paper. Part 6. Missing energy in the title of the paper. By the late 1970s, the theory that unified electromagnetism with the weak nuclear force had been worked out, and it was making a very specific and very testable demand. If the theory was right, there had to be 3 heavy particles carrying the weak force, in the same way that the photon carries electromagnetism. 2 of them would be electrically charged, called the W+ and the W-. One would be neutral, called the Z, and unlike the photon, which is massless, these would be enormously heavy, something like 80 or 90 times the mass of a proton, which is why the weak force is weak and short-ranged rather than reaching across the universe the way electromagnetism does. Nobody had ever seen one. Producing a particle that heavy requires concentrating a great deal of energy in a very small space, and no accelerator on Earth could do it. So CERN did something audacious. It took the superproton synchrotron, an accelerator that had been built to fire protons at a fixed target, and rebuilt it into a collider, so that instead of protons hitting stationary matter, protons would hit antiprotons coming the other way. That change alone multiplies the useful energy enormously, because in a head-on collision between equal and opposite beams, all of the energy is available for making new things, whereas firing at a fixed target wastes most of it pushing the target forward. There was one problem with that plan, and it was a very large one. Antiprotons do not occur naturally in any useful quantity. You have to make them, one at a time, by smashing protons into a target and sifting through the debris, and what you get out is a thin, hot, badly behaved spray of particles going in slightly different directions with slightly different energies, which is exactly the opposite of the tight, cold, well-collimated beam a collider requires. The man who solved that was Simon van der Meer, and his solution, called stochastic cooling, is one of the cleverest pieces of accelerator physics ever devised. You put a sensor at one point in the ring that detects the average deviation of the particles passing it, you send a correction signal across the diameter of the ring, arriving before the particles do because the signal travels in a straight line, and the particles travel around the curve, and you apply a tiny nudge that pushes them back toward the ideal orbit. You do this millions of times. Gradually, statistically, the beam cools and tightens until it is usable. Without stochastic cooling, there is no antiproton beam, and without an antiproton beam, there is no discovery. Now, the signature. The theory predicted that a W boson once produced would decay almost immediately, and one of its cleanest decay channels was into a charged lepton, an electron or a positron plus a neutrino. Read that again and notice the problem. The electron is visible, it is charged, it curves in a magnetic field, it dumps its energy in the calorimeter. It is about the easiest object in particle physics to identify with confidence. The neutrino is not visible. It is the poltergeist from the last section. It goes straight out through everything. So the experimental signature of one of the most consequential discoveries of the 20th century was this: a single electron flying off with a large amount of transverse energy, and directly opposite it, nothing at all. That is why the UA1 detector was built the way it was built. It was designed for coverage approaching the full solid angle around the collision point, wrapping the beam as completely as the engineering of the day allowed, and it was designed that way specifically because a missing energy measurement is only as good as your confidence that you saw everything else. If you have a hole in your detector, you cannot tell the difference between a neutrino and a particle that went through the hole. The entire architecture of the experiment was shaped by the need to trust an absence. It is worth appreciating what the collaboration was up against in terms of sheer rarity. At the energies available, a W boson was produced in something like 1 collision in 10 million, and only a fraction of those decayed into the clean electron channel they were looking for. Then the electron had to land in a well-instrumented part of the detector, and the event had to survive the trigger, and the analysis had to be confident that the electron was really an electron rather than a jet that happened to fake one. By the time all of those factors had multiplied together, a year of running at the world's most advanced collider yielded a handful of candidates, not a distribution. A handful you could name individually and discuss by number over lunch. On the 20th of January 1983, Carlo Rubbia gave a seminar at CERN and presented 6 candidate events. Let me put you in that room. It is winter in Geneva. The auditorium is full, and it is full in the specific way that a room gets full when word has gone around, with people standing along the back wall and sitting in the aisles. Rubbia is at the front, and Rubbia is not a calm speaker. He is famously intense, fast, driving, a man who has spent years pushing an entire laboratory toward this moment against considerable skepticism. And what he puts on the screen is 6 events. 6, not 6,000, not 600, 6 collisions, out of many millions recorded, each one displayed as a diagram of the detector with the reconstructed tracks drawn in. In each of them, there is an electron with a large transverse energy, and there is a great deal of empty detector on the opposite side, and there is a calculated vector pointing into that emptiness with a magnitude that balances the electron almost exactly. What Rubbia is asking the room to accept is not that they have seen the W boson. Nobody has seen the W boson. It decayed long before it could reach any instrument. What he is asking them to accept is that they have seen an electron, and that on the far side of it they have seen nothing, and that the nothing has precisely the right shape and precisely the right size, 6 separate times, to be the fingerprint of a particle whose mass the theory had predicted in advance. He's asking a room full of physicists to accept a whole as evidence. And they did, but not on his word alone, and the reason they did is the part of this story I find most instructive. The UA1 collaboration had not run one analysis. It had run 2, deliberately independent of each other. One approach used a very stringent selection on the electron itself, identifying candidates by the quality of the electromagnetic signature, and then asking what else was in the event. The other approach, developed by the group at Saclay, went at it from the opposite end. It is called the missing energy method, and it did not select on the electron at all. It selected on the imbalance, looking for events with a large amount of unaccounted for transverse energy, and only then asked what visible objects were sitting there. 2 teams, 2 philosophies, one starting from the thing you can see, one starting from the thing you cannot. And when they compared notes, both methods had converged on the same 5 events. 6 events from the first method made it into the final paper. There is a detail about that convergence worth dwelling on. The 2 methods were not just different in technique, they were different in what they could fail at. A stringent electron selection can be fooled by a jet that mimics an electron, but it is not much affected by mismeasurement of the rest of the event. A missing energy selection is exactly the reverse. It barely cares what the visible object is, but it is extremely vulnerable to any part of the detector quietly underreporting energy. The failure modes of the 2 approaches have almost nothing in common, which means that when both of them landed on the same 5 collisions out of many millions, the probability that a shared instrumental artifact had produced the result, rather than a real particle, became very difficult to argue for. That is not luck. That is a designed defense, and it is the same defense in a far more elaborate form that the modern experiments run today. That paper was submitted and published with remarkable speed and appeared on the 24th of February 1983 in the journal Physics Letters B. And I want to read you its title, verbatim, because the title is the whole point of this section. Experimental observation of large transverse energy electrons with associated missing energy at root s equals 540 giga-electron volts. Missing energy, in the title, of the paper, announcing the discovery of the carrier of one of the four fundamental forces of nature. The following year, in 1984, Carlo Rubbia and Simon van der Meer received the Nobel Prize in Physics, and the citation credited the decisive contributions to the large project, which led to the discovery of the field particles W and Z, communicators of the weak interaction. There is an instructive contrast waiting a few months later in the same story. The Z boson was found by the same experiment before the year was out, and finding it was, comparatively speaking, easy, because the Z is neutral, and one of its decay channels produces two charged leptons and nothing else. Two visible tracks opposite each other, with a combined mass that jumps off the plot. No inference required, no whole to interpret. You can practically see it with your eyes, which is exactly why the W was the more instructive discovery. The easy one taught us the mass of a particle. The hard one taught us that a carefully measured absence, cross-checked by two independent methods and backed by an instrument built to see everything else, is evidence you can stake a Nobel Prize on. So the method works. It has been vindicated twice at the highest possible stakes, once over 26 years and once over 6 events. Which raises the question that has been sitting quietly underneath this whole conversation, and which we can no longer avoid. How on earth does anyone know that a particular hole is real? Part 7. How you know a hole is real. Here is the uncomfortable inversion at the heart of this technique. If absence is your signal, then anything in the universe that manufactures a false absence is your enemy, and the list of things that manufacture false absence is long and unglamorous, and almost entirely made up of problems that have nothing to do with physics. Let me walk you through it, because the list is genuinely more revealing than the physics it protects. Start with the beam itself. The pipe the protons travel through is a very good vacuum, better than the vacuum in the space between planets, but it is not a perfect vacuum. There are still stray molecules in there, and every so often a proton, instead of meeting another proton at the collision point where the detector is watching, meets a molecule of residual gas somewhere else entirely. That is a beam-gas interaction, and it sprays particles into the detector from a position and a direction the reconstruction software is not expecting. The result is energy appearing in the calorimeter that has no partner anywhere, and an imbalance that looks exactly like something invisible flew out. Then there is the halo. The proton beam is not a perfectly clean pencil of particles. Around the core there is a diffuse cloud of stragglers, and as those interact with collimators and machine components upstream, they produce muons that come sweeping into the detector cavern, travelling roughly parallel to the beam. A halo muon does not radiate outward from the collision point like everything else. It crosses the detector sideways, laying down a streak of energy along a path that no real collision product would ever take. If the reconstruction picks that up and includes it in the sum, the books stop balancing. Then there are cosmic rays. High above your head, right now, particles from deep space are slamming into the upper atmosphere and producing showers, and the most penetrating products of those showers are muons. They come down through 100 meters of rock into the Atlas cavern at a rate of a few per second, whether or not the accelerator is running at all. In fact, the detector was commissioned using them before a single proton ever circulated, because they were the only particles available. Most of the time they are harmless, but a cosmic muon that happens to cross the detector during the specific 25 nanosecond window of a recorded collision will be reconstructed as though it belonged to that collision, and it did not, and now your ledger is wrong. Then there is noise. There are roughly 100 million readout channels in that detector, and every one of them is an electronic circuit with a floor of random fluctuation. Random noise is manageable. It averages away. What is genuinely dangerous is correlated noise, where a group of neighboring channels fluctuate together, because a group of neighboring channels reporting energy at the same moment is precisely what a real particle looks like. Correlated noise can impersonate a deposit, And if it impersonates 1 on the wrong side of the detector, it creates an imbalance out of nothing at all. And then there is the worst one, which is not an intruder at all. It is your own detector underreporting. Fake missing energy is produced inside the calorimeter routinely by ordinary mismeasurement of ordinary objects. A jet whose energy is underestimated by 20% leaves a corresponding hole in the sum. A tau lepton reconstructed badly does the same, and the most common reason for that kind of underestimation is not electronics or calibration. It is that some of the energy went somewhere the detector is not instrumented. Because real detectors are not seamless spheres. They cannot be. They are built in pieces, and pieces have edges. There is a mechanical boundary where the barrel calorimeter, the cylinder wrapped around the beam, meets the end cap calorimeters that close off the two ends. There is another boundary where the end cap meets the forward calorimeter. Cables have to run somewhere. Cryogenic services for the liquid argon have to enter and leave. Support structures have to hold 7,000 tons of equipment off the floor. Every one of those necessities is a place where a particle can pass through material that does not record it. Now sit with the symmetry of that for a moment, because it is genuinely unnerving. Perfectly ordinary energy, from a perfectly ordinary standard model process, disappearing for the most boring reason imaginable, which is that it went through a gap around a cable, produces a signature that is indistinguishable, event by event, from the most exciting result in modern physics. So what do you do about it? You build an apparatus of suspicion, and it is remarkable. The first tool is timing. Every subsystem records not just how much energy arrived, but when it arrived, to within a fraction of a nanosecond. A particle from the collision arrives at a given calorimeter cell at a known time, because you know where the collision happened and you know the speed of light. Anything arriving early or late did not come from the collision. That single check kills most cosmic rays and most out-of-time beam background outright, and it is such a clean discriminator that the timing calibration of the calorimeters is treated as a critical piece of physics infrastructure rather than a technicality. The second tool addresses punch-through. Sometimes a jet is so energetic that its shower is not fully contained by the calorimeter, and particles come out the back into the muon system, where they get reconstructed as muons that were never there. The tell is that a genuine muon deposits very little in the outermost calorimeter layers, while a punch-through jet lights them up. So you look at the outer layers, and if there is an unusually large deposit sitting just inside your supposed muon, you know what you are actually looking at. The third tool is geometric, and I need you to pay close attention to this one, because it comes back later in a way that will change how you feel about it. Events are rejected when the missing momentum vector points close in angle to a high momentum jet. The reasoning is impeccable. If a jet is mismeasured, if the calorimeter underreports its energy, then the imbalance you create points directly along that jet's direction, because that is where the missing energy went. So a red line lying close to a jet is the classic fingerprint of a mismeasurement. Physicists have seen it thousands of times. It is one of the most reliable warning signs in the business, and events with that topology are routinely thrown out. Remember that. Just file it. We will come back to it. The fourth tool is the simplest. Jets that point at known dead regions of the calorimeter, at channels that are switched off or damaged or missing, are removed from consideration entirely. If the energy went where you cannot see, you do not get to make claims about it. And there is one more thing working against the measurement, running continuously, which is not a fault at all but a consequence of success. It is called pile-up. To produce rare events at a useful rate, you do not collide two protons at a time. You collide dense bunches containing something like 100 billion protons each, and when two of those bunches pass through one another, you do not get one collision. During run 3, you got 60 to 70 separate proton-proton interactions, simultaneously, in the same 25 nanosecond window, all of them recorded by the same detector as a single event. One of those 60 or 70 might be the hard collision you care about. The other 69 are soft, uninteresting, glancing encounters that produce low-energy debris in every direction, and every scrap of that debris lands in the transverse plane and gets added to your sum. This is why the soft term is so difficult, and it is why the missing momentum measurement gets harder rather than easier as the machine gets better. Improving the collider means more collisions per crossing, which means more uncorrelated junk piled on top of the one balance equation you're trying to solve. The tightest working point exists precisely to fight this, and it improves resolution under heavy pile-up conditions by up to 39% relative to the loosest. But no amount of cleverness makes the problem go away. The instrument's own success is the thing degrading its most delicate measurement. And then, underneath all of that, there is the question of how you calibrate the thing at all. How do you know your missing momentum measurement is accurate when, by definition, you have no independent way to know what the true answer was? The answer is beautiful. You find a class of collision where you already know the true answer is 0, and you measure how far off you are. Specifically, you use events where a Z boson was produced and decayed into two leptons, an electron pair or a muon pair. Those are exquisitely well-measured objects, and the standard model tells you with high confidence that there is no invisible particle in that event. So whatever missing momentum you calculate in a sample of those events is not physics. It is your own instrumental error laid out for you to study. That is how the numbers get quoted. Using 140 inverse femtobarns of collisions recorded between 2015 and 2018, Atlas characterized the soft component of the measurement, the crumbs, and after a long program of improvements reduced the systematic uncertainty on its scale by up to 76% and on its resolution by up to 51% compared with the previous calculation. Those are not small refinements. That is most of the uncertainty on the hardest part of the measurement, removed by people who spent years on it, and whose names appear on a 40-page author list. Now step back and look at that whole list of countermeasures together, because I think it is the most quietly moving thing in this entire subject. An enormous fraction of the intellectual effort of a missing energy analysis is spent constructing reasons to disbelieve your own most exciting events. Think about the psychology of that. You're a physicist. You have spent years of your life on this. You're looking at an event with a colossal amount of missing momentum, the kind of event that could be the beginning of the biggest discovery since the Higgs. And your training, your collaborations culture, and the entire published methodology of your field all direct you to do one thing first, which is to try as hard as you possibly can to destroy it. Was there a dead channel there? Check the timing. Was the beam behaving? Pull the halo monitors. Is the jet near the vector? Does it survive the tight working point as well as the loose one? Run it again. The default posture toward a spectacular absence is not wonder. It is suspicion. That is what integrity looks like when it is built at industrial scale, and it is also, very quietly, the reason discovery in this field is so slow. There has never been a false dark matter headline out of a collider, and the reason there has never been one is that thousands of people spent their careers building an apparatus whose deepest function is to catch themselves being wrong about a whole. But an apparatus that good raises a question that nobody in the field particularly enjoys being asked, and it is this. A filter that effective at removing what should not be there is also necessarily capable of removing something that should. So what exactly does it throw away? Part 8, 9999. Let us step back for a moment and put the pieces together before we go any further, because we have covered a lot of ground, and the next thing I have to tell you lands harder if you're holding all of it at once. We have a collision between two protons that are not really objects, whose internal momenta are known only as probabilities. We have one plane, the transverse plane, in which the arithmetic is exact and the books must balance to 0. We have a technique that adds up everything visible and assigns the remainder to something invisible, drawing a red line into a region of the detector where nothing happened. We have 3 historical vindications of that technique, one of which took 26 years and one of which won a Nobel Prize with the words missing energy in the title. And we have an apparatus of institutional doubt built over decades, whose entire purpose is to stop anyone from believing in a hole that is not there. Good. That is where we stand. Now let me tell you about the number that changes the emotional temperature of this whole subject. Inside that detector, bunches of protons cross one another 40 million times every second. 40 million per second. That is the raw rate at which the experiment is offered opportunities, and in the language of engineering it is a bunch crossing rate of 40 megahertz. Nothing on this planet can record 40 million complex detector snapshots per second. Not in 2026, not in 2050. A single fully built Atlas event is a couple of megabytes of data. 40 million of them per second would be something like 80 terabytes every second, which is more data every second than most organizations on Earth store in total. It is not a funding problem or an engineering problem. It is simply not possible, and it never will be. So the experiment does the only thing it can do. It decides, in real time, what to keep. The first stage is called the Level 1 trigger, and it is built out of custom electronics rather than ordinary computers, because ordinary computers are far too slow. It receives coarse granularity information from the calorimeter and the muon system, a blurred and simplified version of what the detector actually saw, and it identifies regions of interest, and it makes a decision. That decision must be reached within a few microseconds, because for those few microseconds the full detector data is being held in temporary buffers, and if the answer does not come back before the buffers fill, the data is overwritten regardless. Level 1 cuts the rate from 40 million events per second down to 100,000. The second stage is called the high-level trigger, and it is a computing farm of roughly 60,000 physical processing cores sitting in a building on the surface. This stage does have time to think, relatively speaking. It runs reconstruction algorithms of nearly the same quality as those used in final offline analysis on the full granularity detector data, and it makes the real decision. It cuts the rate down again to around 1,000 fully built physics events per second during run 2, and up to about 3,000 per second in run 3, along with some additional streams that save partial information about events that could not be kept in full. So let me state the consequence as plainly as I can. The Atlas trigger discards roughly 9,999 out of every 10,000 events the detector sees. And I need to be precise about what discarded means here, because people often assume it means something gentler than it does. It does not mean archived at lower priority. It does not mean compressed and stored on tape somewhere in a warehouse. It does not mean written to a summary file for later. The data exists in a buffer for a few millionths of a second. A machine looks at it. The machine decides no, and it is overwritten by the next event. There is no copy. There is no backup. It is gone, permanently, having been judged not worth keeping by an algorithm running faster than any human being could form a thought. Now, the trigger is not a scandal. I want to be completely clear about that, because this is exactly the sort of fact that gets pulled out of context and turned into something it is not. The trigger is not hiding anything. Its logic is published in detail, in documents anyone can read, and it is the only reason the experiment can function at all. Without it, there is no data, no Higgs boson, no physics, nothing. Every collider experiment ever built has had one, but it does have a consequence that is unavoidable and worth stating carefully. The collider does not record what happened. It records what it was told in advance to consider worth recording. The list of things it was told to consider worth recording is called the trigger menu. It is a curated inventory of specific signatures, each with its own thresholds, negotiated and written down before the run begins and revised between runs, high-energy electrons above a certain momentum, muon pairs in a certain mass window, jets above a threshold, and relevant to us, events with missing transverse momentum above some minimum value. That menu is, in a very real sense, a physical embodiment of the collaboration's collective theoretical expectations at the moment the run started. It is what a few thousand of the best physicists in the world believed, years in advance, was most likely to be interesting, and it is a fine list. But it is a list. There is a way of feeling the scale of this that I find helpful. Imagine a library that receives 40 million books every second. It has room on its shelves for 3,000 of them. A machine at the door reads the spine of each book in a few microseconds, compares the title against a list drawn up years earlier by the librarians, and either shelves it or feeds it into an incinerator. The machine is fast, it is fair, it applies its rules consistently, and the rules were written by thoughtful people who knew a great deal about books. But the list was written before this particular delivery arrived, and a book with a title nobody had thought to put on the list burns exactly as fast as one that was already there in 10,000 copies. That is not a criticism of the librarians. There is no alternative arrangement. You cannot keep 40 million books a second, and a machine that hesitates burns the whole delivery while it thinks. But it does mean the library's collection is not a sample of the books that arrived. It is a sample of the books that were expected. The missing energy triggers are among the hardest ones to run, for a reason we have already met. Pile-up drives their rates up steeply. All that uncorrelated debris from 60 simultaneous soft collisions produces a background of moderate fake missing momentum, and that background is enormous, and if you set your threshold too low, your trigger fires constantly and swamps the bandwidth, so the threshold gets raised. And raising a missing energy threshold by a few tens of billions of electron volts can quietly remove an entire category of possible new physics from the recorded dataset forever, without anyone involved ever knowing that it happened. The field is not blind to this. There are countermeasures, and they are ingenious. There is a technique called data scouting, or trigger-level analysis, where instead of throwing an event away entirely, you save a drastically reduced summary of it, just the reconstructed objects from the trigger itself, a few kilobytes instead of a few megabytes, so that you can at least do statistics on classes of event you could never afford to keep in full. There is a growing effort in machine learning anomaly detection, which we will come back to. But these are patches on a fundamental situation, and the fundamental situation does not change. And there is a second-order effect that is easy to miss, because the trigger menu reflects what physicists expected, and because analyses can only be performed on data the trigger kept, the results of those analyses feed back into what the next trigger menu is written to look for. A field that finds nothing in the places it looked will, quite reasonably, keep looking in those places with better precision. The loop is not vicious, and everyone involved is aware of it, but it is a loop, and loops have a way of becoming grooves. I want to sit in this for a moment, because I think it is the coldest fact in tonight's story, and it is not the one people expect. Over the 4 years of Run 3, an almost incomprehensible number of proton collisions occurred inside that detector. Each one was real. Each one was examined by machines for a few millionths of a second, and the overwhelming majority of them were erased forever, without any human being ever knowing they had existed, without a record, without a trace, without a name. If something genuinely new happened in one of those collisions, and it did not resemble anything the trigger menu had been written to notice, then it did not merely go unnoticed, it went unrecorded, and the machine is off now. There is no going back and checking. There is no reprocessing the raw data, because there is no raw data. That particular event happened, once, 100 meters under a field in Switzerland, and then it was gone. That is not a conspiracy. Nobody covered anything up. It is something stranger and more permanent than that. It is a limit on what a finite instrument can know about an infinite stream of events, and we ran into it decades ago and we have been living with it ever since. So that is what was thrown away. Now let us talk about what survived and what it showed. Because the searches did happen at enormous scale, and the results are not what most people assume. Part 9, 50 searches and no excess. If something exotic is being produced in those collisions and leaving without touching anything, then missing transverse momentum is the most direct handle anyone has on it. Not an indirect hint, not a subtle deviation in a decay rate, the thing itself, escaping, leaving its own shape behind in the balance sheet. So people looked, exhaustively, systematically, for well over a decade, with the full resources of the two largest experimental collaborations in the history of science. It is worth being clear about why anybody expected to find anything in the first place, because the expectation was not arbitrary. Astronomers have known for the better part of a century that galaxies do not behave as though they contain only the matter we can see. Stars at the outer edges of spiral galaxies orbit far too quickly for the visible mass to hold them. Clusters of galaxies move as though bound by several times the gravity their glowing contents could supply. The way light bends around massive clusters maps out far more mass than the light accounts for, and the pattern of ripples in the leftover heat of the Big Bang requires a component of matter that does not interact with light at all. 5 separate lines of evidence, from completely different eras and completely different instruments, all pointing at the same conclusion, which is that roughly 5/6 of the matter in the universe is something we have never identified. And there was a specific reason to think a collider might make some. If that missing matter is a particle that interacts through the weak nuclear force, and has a mass in the general vicinity of 100 times the protons, then the amount of it left over from the early universe works out, from a straightforward calculation, to be almost exactly the amount astronomers observe. That coincidence has a name. It is called the WIMP miracle, and for 30 years it was the single most persuasive argument in the field, because it suggested that the answer to a cosmological question might be sitting at exactly the energy scale we were about to be able to reach. The flagship search is called the monojet, and I want to describe it carefully because the physical picture is genuinely strange. Imagine that a collision produces a pair of invisible particles and nothing else. 2 dark matter candidates, say, flying out back to back. What does the detector see? Nothing. The 2 invisible particles balance each other in the transverse plane, so there is no imbalance to measure, and there is no visible object anywhere. The event is completely empty. It does not even trigger. It is not that you would fail to identify it. It is that there is nothing there to identify. A perfect invisible production event is, from the detector's point of view, indistinguishable from a collision that never happened. So how do you ever see one? You get lucky. Occasionally one of the incoming partons radiates a gluon just before the collision, the same way an accelerating electric charge radiates a photon. That gluon becomes a jet, flying off in some direction, and now the invisible pair has to recoil against it to conserve momentum. Suddenly there is one visible object in the detector, a single energetic jet, and directly opposite it, a large quantity of missing transverse momentum and nothing else at all. One jet, one red line, an otherwise empty detector, which means the entire strategy for detecting the most sought-after invisible particle in physics depends on the machine happening to sneeze at the right moment. The invisible thing is only visible because of an accident that had nothing to do with it. There is a version of that fact that is funny, and a version that is bleak, and I think both are true. There is a variant called the monophoton, which works the same way but with the initial state radiating a photon instead of a gluon. Photons are rarer, so you get fewer events, but a single photon in an otherwise empty detector is a much cleaner signature than a jet, so you trade rate for clarity. There are mono-Z searches, mono-Higgs searches, mono-top searches. Every one of them is the same idea with a different visible chaperone, and then there are the model-specific versions. Searches for a heavy mediating particle, an axial vector or a pseudo-scalar that couples to both ordinary matter and dark matter and decays into a dark pair. Searches for a Z-prime, a heavier cousin of the Z boson, acting as a bridge to a hidden sector. Searches for supersymmetric particles whose lightest member is stable and invisible. Searches for extra-dimensional gravitons escaping into space we cannot access. Between them, Atlas and CMS have published more than 50 analyses sensitive to dark matter production at a collider. Not one of them has found a significant excess of data over the expected standard model background. Every single one. Consistent with nothing new. 50+ different ways of drawing the red line, 50+ different definitions of what the interesting kind of nothing would look like, and every time the number of events observed matched the number of events predicted by known physics within the uncertainties. And it is not just the collider. The same conclusion has been arriving independently from a completely different direction. Deep underground detectors have been hunting for dark matter particles from our own galaxy, drifting through the Earth and occasionally bumping into a nucleus. The most sensitive of these, the LZ experiment, completed a 280-day exposure across 2023 and 2024 and found nothing, setting the strongest limits yet achieved and leaving, as the collaboration put it, significantly fewer places for these particles to hide. Roughly 30 years of intensive searching, across colliders and deep mines and space-based instruments, and there is no confirmed detection of a weakly interacting massive particle anywhere. Now, I want to handle this honestly, because there is a lazy way to tell this part and a truthful way, and the lazy way is to call it a failure. It is not a failure. A limit is a result. When an experiment reports that it found nothing, what it is actually reporting is a statement about the universe with real content, which is that a specific set of possibilities is now ruled out. Those 50 analyses have collectively eliminated very large regions of the parameter space that looked most theoretically compelling in 1990. Whole families of models that were entirely respectable when I was born are now dead, killed not by argument but by data. That is progress. It is not the kind that gets a press conference, but it is progress, and it is arguably harder won than a discovery, because a discovery announces itself, and an exclusion has to be earned point by point across an entire plane of possibilities. There is one more thing to say about what a null result costs, which is rarely said out loud. Those 50 analyses represent, conservatively, thousands of person-years of work, doctoral theses, careers, people who joined the field at 22 because they wanted to be in the room when dark matter was found, and who are now in their 40s, and who have written beautiful, rigorous, technically superb papers reporting that they found nothing. That is not a tragedy, and they would not thank me for framing it as one. But it is a real thing that happened to real people, and the reason they kept doing it is worth naming, which is that the alternative to looking carefully is not looking at all. But there is one detail in how these searches are limited that I find quietly perfect, and it is the reason I wanted to spend a whole section on this. Monojet searches are not limited, in the end, by how many collisions you have. They are limited by how precisely you can predict the background. And the dominant irreducible background to a monojet search is a process where a Z boson is produced alongside a jet, and the Z boson decays into two neutrinos. Look at what that event is. One jet plus a pair of particles that leave no trace carrying away momentum. That is not similar to the signal. That is the signal, produced by entirely ordinary, entirely understood, entirely standard model physics. The only way to tell the two apart is statistically, by predicting with extreme precision how many of the ordinary ones you should have and looking for a surplus. So the thing that limits our ability to find a new invisible particle is an old invisible particle we already know about. Pauli's desperate remedy, 96 years later, is the wall. The ghost he invented to save energy conservation is now the single largest obstacle standing between us and the next ghost. I do not think there is a tidier illustration of how physics actually proceeds than that. Where has the field gone in response to all these nulls? Not into retreat, into breadth. The weakly interacting massive particle was always the favourite because it had an elegant argument behind it, but it was never the only candidate, and the null results have driven an enormous interest in alternatives. Axions, which are extraordinarily light and would be detected by completely different methods. Primordial black holes formed in the first instance of the universe. Fuzzy dark matter, so light that its quantum wavelength is the size of a galaxy. Entire dark sectors with their own forces and their own structure, which we will get to in a moment because they matter enormously for this story. Every one of those 50 analyses is the same red line, drawn a different way, and every single time it pointed at nothing more interesting than the emptiness we already understood. But there is one number in this program that is not a clean null. There is one measurement where the door is very conspicuously ajar, and it concerns the most famous particle discovered in your lifetime. Part 10. 1 in 10. The Higgs boson was discovered in 2012, and in the years since the job has changed from finding it to interrogating it. And the most interesting thing you can do with a particle you have found is count what it turns into. The Higgs is unstable. It exists for something like a sextillionth of a second and then it decays, and the theory makes very precise predictions about the proportions. So many percent into pairs of bottom quarks, so many percent into W bosons, so many into tau leptons, a small but crucial fraction into pairs of photons, which is how it was found in the first place. Add up all the predicted channels and you should get 100%. If you measure the rates and they add up to less than 100%, then the Higgs is doing something the theory does not know about, and there is one very specific something it might be doing. The Higgs boson is, for reasons rooted in the structure of the theory, an unusually good candidate for a bridge between our world and a hidden one. Most particles cannot couple to a new neutral particle without violating a symmetry that we know holds. The Higgs can. Its coupling structure permits a direct connection to a neutral particle carrying no charge under any of the forces we know, without breaking anything. Physicists call this idea the Higgs portal, and it is not a fringe suggestion. It is one of the most studied frameworks for connecting ordinary matter to whatever the dark matter is, precisely because it requires so little. So if the Higgs is a portal, then some fraction of the Higgs bosons produced at the collider should decay into things that leave no trace, which means a Higgs production event with absolutely nothing coming out. And now you know exactly how to look for that, because it is the same technique we have been building all night. You cannot see a Higgs that decays invisibly, so you find the Higgs some other way, and then you look at what does not come out. Atlas combined several approaches. The most powerful is vector boson fusion, where the Higgs is produced by two quarks each radiating a heavy boson, which then merge. That process leaves a distinctive signature, because the two quarks continue forward and produce two jets far apart in the detector, widely separated in angle, with relatively little activity between them. Those two forward jets are a tag. If you see them, and you see a large missing momentum vector, and you see essentially nothing else, that is a candidate. They also used a variant with an additional photon in the final state, and gluon fusion production accompanied by a jet from initial state radiation, an associated production where the Higgs is made alongside a W or Z boson that decays into leptons you can see. It is worth pausing on how peculiar the vector boson fusion signature actually is when you picture it. Two protons pass through one another. From each of them, a single quark emits a heavy force carrier and is deflected slightly, continuing on its way at a shallow angle and eventually becoming a jet far down the detector, close to the beam direction. The two emitted force carriers meet in the middle and fuse into a Higgs boson. So what the detector records, if the Higgs decays into nothing, is two jets sitting far apart near the two ends of the machine, a wide empty gap between them where the Higgs quietly happened and quietly left, and a red line in the transverse plane accounting for a particle whose entire existence is inferred from a hole between two glancing blows. There is something almost absurd about it. The most sensitive test of whether the Higgs boson talks to the dark universe is conducted by carefully measuring two pieces of debris that were not really involved. 4 production modes, 139 inverse femtobarns of collisions at 13 trillion electron volts, and here is the result. The upper limit on the fraction of Higgs bosons decaying into invisible particles is 10.7% at 95% confidence. The expected sensitivity, meaning what they anticipated being able to achieve before looking, was 7.7%. Now let me tell you what the standard model predicts, because that is where this stops being a technical number and starts being something you feel. The theory does allow the Higgs to decay invisibly, by a roundabout route. It can decay into 2 Z bosons, and each Z can decay into a pair of neutrinos, and neutrinos are invisible. So the predicted invisible fraction is not 0. It is about 0.1%, 1 in 1,000. The measurement cannot exclude 10.7%. That is a factor of 100 of unexplored room, which means, stated as carefully and as honestly as I can, that as things currently stand, up to roughly 1 Higgs boson in every 10 could be decaying into something nobody has ever seen, something that carries energy out of the collision, and out of the detector and out of the building, and the most sensitive experiment ever built cannot rule it out. Let me put you inside that gap for a moment. Imagine a room with one door. You're standing at the door with a counter, and your job is to know where everybody is. People go in, people come out, you count both, and at the end of the day the numbers agree, mostly. For 9 out of every 10 people who walked in, you can point to the moment they walked out. You know their faces, you know the time, you have it written down. The 10th person you cannot account for. They went in. You're certain of that. You have no record of them leaving. And here is the part that changes it from a curiosity into something colder. It is not that you were not paying attention. It is not that you need a better counter, or a brighter light, or more staff. It is that this room has exactly one door, and you are standing at it. And by the design of the room, standing at that door is the only observation you are able to make. If there is another way out, you cannot find it by counting harder. You would have to leave the door. That is where physics is standing right now with the Higgs boson. 9 times out of 10, we know precisely where everything went. The 10th we cannot account for, and the measurement that would account for it does not exist yet. I have to add the qualification that intellectual honesty demands, and it matters. This is not evidence that 10% of Higgs bosons are vanishing. It is not a hint, and it is not an anomaly, and anyone who tells you it is a hint is overselling it. It is an upper limit, which is a statement about the sensitivity of the experiment rather than a statement about the world. The measured value is entirely consistent with the standard model's 1 in 1,000. What the limit says is that if a large invisible fraction existed, we could not yet tell. The window is not evidence of something in the room. It is evidence of how much of the room we cannot see. But that is precisely why it is worth taking seriously, and there is a detail that makes it more than academic. For dark matter particles lighter than about 60 billion electron volts, this collider limit on the Higgs is actually more constraining than the results from those deep underground detectors buried beneath mountains. In that mass range, watching what the Higgs does not turn into tells you more about dark matter than watching a tank of liquid xenon, a kilometre below the surface of the Earth. The accelerator beats the mountain by counting absences. There is a reason this particular measurement is more powerful than it looks, and it comes down to the Higgs being narrow. The Higgs boson's natural decay width is tiny, only about 4 millionths of its mass, which means that even a modest new decay channel makes a large proportional difference to how it behaves. A new invisible mode at the 10% level would be almost invisible in most other measurements, buried inside the uncertainties on everything else. But counted directly, as an absence, it stands out. That is a general lesson worth carrying away from tonight. There are questions where measuring what is there is hopeless, and measuring what is not there is the only sensitive method available, and what would close the window. More data, measured more precisely, which is exactly what the high luminosity upgrade is for, and exactly what will not exist until sometime in the 2030s. The question sits open, in a machine that is currently switched off, and it will sit open for years. If that window turns out to be real, then think about what it would mean. A measurable fraction of the most famous particle ever discovered has been quietly leaking into a part of reality nobody has ever observed. Not in some distant galaxy. In a machine that human beings designed and built and paid for, 100 meters beneath a Swiss field, for more than a decade, while thousands of people watched it happen. And that, remember, is the good case. That is the case where the escaping thing at least has the decency to produce missing energy that we know how to look for. There is a worse case. There is a category of thing that could be produced in those collisions and leave, and not only would we not detect it, we would actively delete the evidence ourselves, using a procedure that is entirely correct. Part 11. The signal we would delete. There is a category of possibility that unsettles me more than an unfound signal, and it is a signal that the analysis chain is built to remove. To get there, I need to introduce an idea about what the dark sector might actually be, because almost everything you have ever heard about dark matter quietly assumes the simplest possible version, and the simplest possible version might be badly wrong. The standard picture is that dark matter is one kind of particle, a single species, stable, electrically neutral, drifting through the galaxy, occasionally bumping into something. That is the picture behind every monojet search we discussed, and it is a perfectly reasonable place to start because you always start with the simplest thing that could work. But look at the matter we do understand. Ordinary matter is not one particle. It is 6 flavors of quark and 6 leptons and 4 kinds of force carrier and a Higgs boson, bound into protons and neutrons and atoms and molecules, with a rich internal structure and its own forces and its own physics. Why on earth would the other 5/6 of the universe be simpler than the 6th we live in? Theories that take that question seriously are called hidden valley models. They were developed in the mid-2000s, and the idea is that the dark sector is not a lonely particle but a whole world, with its own force, its own charged states, its own bound objects, connected to our world only by some very narrow bridge, some heavy mediating particle or some small mixing that lets the two sectors barely notice each other. Here is what changes if that is true. If you produce a dark sector particle in a collision, it does not simply fly out. It cannot, for exactly the same reason a quark cannot. If the dark force behaves anything like the strong force, then pulling a dark particle away from its partner costs escalating energy until the vacuum simply makes a new pair, and then those split, and then those split, and what you get is a cascade. A dark parton shower, the dark sector's own version of a jet, and a dark shower does not contain one kind of thing, it contains a population. Some of those dark-bound states are stable and genuinely invisible, and they leave. But some of them can decay back into ordinary particles through the narrow portal that connects the two sectors, producing perfectly normal pions and electrons and photons that the detector sees without difficulty. So what arrives at the calorimeter is a jet, in the ordinary sense a collimated spray of visible particles. But its energy is systematically short, because a fraction of the original shower left without depositing anything. It is a jet with holes in it. Physicists call it a semi-visible jet. And now think about where the missing momentum vector points in an event like that. It does not point away from the jet, out into empty detector, the way it does in the clean monojet picture. The invisible particles were part of the shower. They were travelling in the same direction as everything else in it, so the red line points directly into the jet. Now cast your mind back to part 7, to the third tool in the apparatus of suspicion. Events are rejected when the missing momentum vector points close in angle to a high momentum jet. That cut is correct. I want to be very clear about that, because this is the sort of thing that gets misrepresented the moment it leaves a physics department. The cut is not lazy, it is not an oversight, and it was not adopted carelessly. It exists because that geometry is overwhelmingly produced by mismeasured jets, thousands of times more often than by anything else, and without it the missing energy searches would drown in instrumental noise and could not function at all. It is also the exact configuration a semi-visible jet produces. The cut that protects the measurement is the cut that deletes the discovery. I find that sentence difficult to sit with, and I think it is worth being precise about why. This is not a story about incompetence, and it is not a story about anyone hiding anything. The people who wrote that cut are the same people who published the semi-visible jet papers, or their colleagues down the corridor. This tension is discussed openly in the literature. It is the subject of workshops. Dedicated searches have been designed specifically because of it, searches that deliberately relax the standard cleaning and then work much harder to control the resulting background by other means. But those dedicated searches only exist because somebody first sat down and imagined this particular kind of thing, and the tension is real and it is structural, and it generalizes far beyond this one example, which is why I wanted to spend time on it. Any measurement precise enough to be useful has to define what counts as an error, and that definition is a bet about what kinds of thing exist. Let me give that a more concrete shape, because it is easy to nod along to and hard to actually feel. Suppose you are an ornithologist who has spent your career studying a forest, and you have built a wonderful automated system for identifying birds by their calls. It has one rule you consider foundational, which is that any recording containing the sound of running water is discarded, because the stream that runs through the forest produces a burbling noise that the software repeatedly mistakes for a warbler. That rule is correct. It has saved you from thousands of false identifications. You would defend it in front of a committee. Now suppose there is a bird in that forest, rare and undescribed, that only ever calls from the rocks beside the stream. You will never find it. Not because you were careless, and not because your instrument was insensitive, but because the single most reliable rule you have for distinguishing signal from noise happens to be shaped exactly like the thing you're looking for, and you will not discover this by improving the microphone. The only way you ever find that bird is if somebody, somewhere, first has the thought that it might exist, and then goes and listens beside the water on purpose, knowing they will have to do far more work to sort real calls from burbling. That is the entire situation with semi-visible jets, and it is why the imagination of theorists is not a luxury in this field. It determines what the experiments are capable of noticing, and the semi-visible jet is only the mildest case. Turn one parameter, the lifetime of the dark-bound states, and the picture changes completely. Make them a little longer lived, and they do not decay immediately in the collision. They travel a few centimeters first, and then decay, producing tracks that appear to spring into existence in the middle of the tracking detector, with no connection to any collision point at all. The reconstruction software, which is written on the assumption that charged particles come from a vertex, does not know what to do with a track that starts in mid-air. These are called emerging jets, and they look, on a display, like a jet that switches on partway through. Make them longer lived still. Dark glue balls, bound states of dark gluons with no ordinary matter in them whatsoever, can be extraordinarily long-lived, because decaying requires a high-order process squeezed through a very narrow portal. Such particles can have decay lengths of meters. A particle with a decay length of meters crosses the entire inner tracker, leaving absolutely no trace, because it is neutral, and then decays somewhere out in the calorimeter or in the muon system, producing a burst of energy in a place where, according to everything upstream of it, nothing should be. Make them longer lived than that, and they simply leave. Out through the calorimeter, out through the muon system, out through the rock, gone, having deposited nothing anywhere. So the same underlying theory, with one number dialed from small to large, predicts a continuum that runs from a slightly odd jet, through a jet that begins in mid-air, through a shower of energy erupting out of nowhere in the middle of the detector, all the way to a perfectly empty event where the only sign that anything happened is that the arithmetic quietly does not work. The field is not asleep to this. There is an entire program of searches now aimed at exactly these signatures. Displaced vertices, where you look for decay points far from the collision. Disappearing tracks, where a charged particle's trail simply stops. Non-pointing photons, arriving from a direction that does not lead back to the beam. And there are serious proposals for whole new detectors, built on the surface above the collision hall or in adjacent caverns, whose only job would be to catch particles that decay long after they have left the main apparatus, tens or hundreds of meters away, in places where nothing else could possibly be. And there is the machine learning work, which is the most philosophically interesting response of all. Anomaly detection, in this context, means training algorithms to flag events that are unusual, without ever being told what unusual is supposed to look like, not searching for a specific model, searching for strangeness itself. It is an explicit attempt to escape the trap of only being able to find things somebody thought of in advance, and it is precisely the field that the author of that Atlas blog post moved into. The person who wrote the public explanation of how to measure a hole now works on teaching machines to notice holes nobody described to them first. Every one of these efforts is an attempt to widen the definition of nothing that the red line is allowed to point at, and all of it is fixable. That is the important thing about this entire section. Software can be rewritten, cuts can be relaxed, searches can be added, detectors can be bolted on in service tunnels. Every blind spot I have described tonight is, in principle, a blind spot we can do something about. Except one. There is a direction in which nothing can be measured, ever, by any upgrade or any algorithm or any amount of money, and it has been built into that machine since the day it was designed. And unlike everything else in tonight's story, it does not come from a limitation of our engineering. It comes from the geometry of the question itself. Part 12. The Direction We Cannot Look. Early tonight, in the second part, I asked you to set something down somewhere you could find it again. I want it back now. I told you that nobody knows how a proton's momentum is divided among its partons at the instant of a collision, that the division is described only by probability distributions, measured over decades but never known event by event. I said it would come back and rearrange everything. Here it is. Consider what you actually know about a single collision at that machine. You know the total energy of each proton precisely, because you built the accelerator that gave it to them. You do not know how much of that energy was carried by the specific quark or gluon that did the colliding. It might have been a third of the proton's momentum. It might have been a 20th. It is different every time, drawn from a probability distribution, and there is no measurement anywhere in that detector that can tell you which value it took, which means the two partons that met did not, in general, carry equal and opposite momentum along the beam. Their collision had a net motion along the beam axis, and you do not know what it was. And now follow that through, because the consequence is severe. If you do not know the initial momentum along the beam, then you cannot balance the books along the beam. You cannot subtract what came out from what went in, because you do not know what went in. The total energy of the collision and the total momentum of the collision are not determinable at a Hadron Collider, not with better electronics, not with a bigger calorimeter, not in principle from the detector's readout at all. This is why the transverse plane was ever singled out. It was never because sideways is special. It is because sideways is the only component we know. The partons carried essentially no momentum across the beam, so the transverse initial condition is 0, and 0 is a number you can do arithmetic with. Every clever thing in tonight's story, every red line, the W boson, the monojets, the invisible Higgs, all of it exists inside that one narrow window of knowability, and the window is narrow because it is the only place where we happen to know what we started with. And the geometry makes it worse. Detectors are least complete precisely near the beam axis, and they have to be, because that is where the beam pipe runs, where the focusing magnets sit, where the accelerator's own machinery occupies the space. You cannot put instruments there. Anything you did put there would be destroyed within hours by the radiation, and it would ruin the beam. The phrase you will find in the literature is incomplete hermeticity close to the beam axis, and it is the polite way of saying that the two places a detector cannot see are the two places it is physically obliged to leave open. So here is the answer to the question I posed at the start of tonight, and I am going to give it to you plainly, without hedging. If something invisible leaves a collision sideways, its absence bends the transverse ledger, and we can reconstruct it. Direction, magnitude, everything, to a precision that is genuinely one of the achievements of modern science. If the same thing leaves along the beam axis, it produces no measurable imbalance at all. There is no arithmetic in physics that can recover it from that detector's readout. It does not register as a small signal, or a difficult signal, or a signal buried in background. It registers as nothing whatsoever, in an event that looks entirely ordinary, and entirely balanced, and entirely fine. The cut that protects the measurement is the cut that deletes the discovery. I said that about a line of analysis code, but the beam pipe is the same sentence, written in steel and vacuum. The thing that makes the collision possible in the first place is the thing that guarantees one direction can never be examined. And this one is not a software choice anybody can revisit. It is not a threshold anybody can lower. It is structural, and it is permanent, and every Hadron Collider that has ever been built or ever will be built has it. Now, I promised you at the beginning that this channel deals in wonder rather than dread, so let me tell you what people did about it, because what they did is the best thing in this entire story. They noticed. Somebody sat down and worked through exactly the reasoning I have just given you, and instead of writing a melancholy paper about the limits of knowledge, they asked a practical question. If everything invisible is leaving along the beam axis, and we cannot put a detector on the beam axis at the collision point, then how far down the tunnel would we have to go before we could? The answer turned out to be 480 metres. 480 metres downstream from the point where Atlas sits, along the line the beam travels, there is a service tunnel. It was not being used for anything. Between that tunnel and the collision point there are hundreds of metres of rock and concrete and magnet steel, and that mass absorbs essentially every particle produced in the collisions, every particle except one kind. So they put a detector there. It is called phaser, and it is small by the standards of this field, a few metres long, a thing you could walk around in an afternoon rather than a cathedral. At its heart is phaser nu, a stack of tungsten plates interleaved with photographic emulsion, which is 19th century technology being used to do something nobody had ever done. Let me take you along the path. You are a neutrino, born in a proton collision at the centre of Atlas, and you are leaving in the forward direction, almost exactly along the beam. In the first fraction of a nanosecond you pass through the silicon tracker, and nothing happens. You pass through the electromagnetic calorimeter, dense enough to stop an electron dead, and nothing happens. Through the hadronic calorimeter, through the magnet coils, through the muon spectrometer, out through the shielding wall. Around you, every other particle from that collision has already been caught and counted and turned into a number. You continue, you pass into the rock, hundreds of metres of it. Solid, undisturbed Jurassic rock beneath a Swiss field, the kind of mass that stops absolutely everything, and you cross it as though it were an open window. You pass through magnets that steer the beam, through concrete, through the walls of a tunnel, and then, 480 metres from where you were born, you meet a plate of tungsten. And this time, for no reason other than luck, you interact. A single nucleus. One collision, out of a number of chances so small it barely deserves the name of a probability. And in the emulsion beside that plate a track appears. A physical mark in a photographic film that can be developed and looked at with a microscope. In the 2022 dataset, phaser recorded 153 of those. 153 muon-neutrino interactions announced in March of 2023. The first neutrinos ever directly detected at a particle collider, anywhere, by anyone. They also caught the first electron-neutrino interactions at a collider, and the neutrinos they detected are the most energetic ever directly observed from an artificial source. A companion experiment, SND at the LHC, does the same job on the other side, and here is the part that turns a fix into a discovery. Those forward neutrinos are not a nuisance that somebody finally caught. They are a physics program in their own right, because they are produced by the decays of particles containing heavy quarks. Streaming out along the beam direction, measuring them tells you about processes at very small angles that no other instrument at that machine can reach. That in turn feeds directly into understanding the highest energy cosmic ray showers in the atmosphere, where exactly the same forward production physics determines what reaches the ground. A blind spot, once someone built an instrument to look into it, turned out to contain a view of something else entirely. That is a pattern worth naming, because it recurs constantly in this field. The neutrino itself began as an accounting embarrassment and became a tool for looking inside the sun. Missing energy began as a nuisance and became a Nobel Prize, and the one direction a collider cannot see turned out, when somebody finally put a detector in it, to be a window onto the physics of cosmic rays arriving from the other side of the galaxy. Sit with the implication of that for a moment. That machine had been running for more than a decade. It had produced neutrinos in quantities beyond any useful comparison, as an unavoidable byproduct of nearly every collision it ever made. And in all that time, not one of them had ever been directly detected there. Not because they were rare. They were the opposite of rare. It was because they were all going in the one direction the experiment cannot look. Everything comes to him who knows how to wait. Perley wrote that in 1956, about 26 years of patience, and it meant something warm. Tonight it means something else. The collider is dark and it will stay dark until 2030. The archive is closed and it cannot be added to. Whatever escaped, escaped, and the only thing left to do is wait and look at what we already have, more carefully than we looked the first time. That is a colder version of the sentence, and there is a chill in it, because there is no guarantee that what we are waiting for is coming at all. But there is a warmer version too, and the warmer version is the one I want to leave you with. The red line points at nothing. That is what makes it the strangest arrow in physics. It is drawn by measuring everywhere else, by accounting so completely for what is present that the shape of what is absent falls out of the arithmetic. And along the beam axis no red line can be drawn at all. There is no measurement to make. There is no hole to describe. For over a decade, that is exactly the direction every neutrino this machine ever made was travelling, in silence, unrecorded through the rock. And when human beings worked out that there was a direction they could not look, they did not stop. They walked 1/2 kilometre down the tunnel, into an empty service passage nobody had a use for, and they built an eye in the dark. So, is something escaping the Large Hadron Collider? Yes, constantly. In quantities you could not count. It has been leaving that machine since the day it switched on, and it left for the last time on a Saturday in June. And the terrifying part was never what it is. We know what most of it is. The terrifying part is the direction it leaves in, and the fact that our best instrument for detecting the invisible turns out to be an instrument that can only ever make its most important measurement sideways. There is a whole hemisphere of that question we have barely started to ask. The machine is quiet now. The rock is still there, and somewhere in a service tunnel, in a stack of tungsten and photographic film, something is still arriving.